Hi there. In this video, we're going to start chapter 4 proper. And it's a pretty long section, so I'm going to get through it as quick as I can. So let's get started. So we're going to try to solve the area problem. All of chapter 4 and then parts of future chapters are concerned with finding areas under curves between endpoints that we draw as vertical lines and above the x-axis. So we're going to try to come up with a method that will find the area under certain kinds of continuous functions. And notice that if we, so this picture here is the main example we're going to use in this section. It's the same one that's in the book, but it's a really nice example. So we have the function y equals x squared, and we want to know, how do I find the area under the curve? Like, how would we do that? So it turns out that this is not an easy problem to solve. This problem was not solved in a very technical, rigorous way until the middle of the 1850s, approximately, which is very new considering Isaac Newton came up with a lot of the calculus before in the 1600s, right? So it's not an easy problem, and what you're going to see is the results of hundreds of years of research. So the big idea is to first approximate the region S by rectangles, and then take the limit of the areas of these rectangles as we increase the number of rectangles. So that's just our general philosophy with this. So if we want to approximate this little S1, we build a little rectangle with, in this case, the right endpoint of the interval telling us the height. And we basically just say to ourselves, if we keep adding lots and lots more rectangles, does the approximation get better and better and better? If it does, that means we can take the limit. And we already know how to do limits. So we're going to look in detail at this right endpoint approximation. So here we have the y value given by the height of the right endpoint. And again, n is the number of rectangles. So if we're doing 4 rectangles, we would call it R4. So that's what we're going to see here. So we're just going to solve this problem. So let's just, think about what's going to happen here. Okay, so we're doing a right endpoint approximation with 4 rectangles, right? You can flip back and look at them. The bases of the rectangles are the intervals 0 to a quarter to a half to 3/4, and 3/4 to 1. And the height is f of x equals x squared, evaluated at the right endpoints of the intervals. So the general idea then, for any R4 on the interval 0, 1, it's going to be, a quarter, because again, these are rectangles, right? This is just base times height of each rectangle. The base is 1/4, right? The width of this first interval is 1/4. The height is the function at 1/4, because this is the right endpoint. And then the next rectangle, the width is 1/4 again, and the height is a half, because that's the right endpoint. So it's the function evaluated at 1/2. So this is a general technique that works for all functions. And you just keep going across, right? Well, notice that this right endpoint approximation, all of the bases are the same. They're all 1/4. That's important that we can factor that 1/4 out, because we're going to do it later when we're doing this with algebra instead of numbers. And then here I'm just evaluating the function. So type that into a calculator, and you get 0.46875. What if we use a left endpoint approximation? What if the heights of the rectangles is given by the left endpoint of the interval? Let's see what happens. So we're going to do example 1 again, but this time a left endpoint approximation. So the bases are still the same. You always want to write out the intervals because you could do left endpoint, right endpoint. You got to be able to see the endpoints. It's really important. So here our left endpoint approximation. So the width is still 1/4 for each rectangle, the base, and the height here is f of 0, the left endpoint, then f of 1/4, left endpoint, right? So it's just all the left endpoints. Again, we can factor that 1/4 out because all the widths are the same. Type it in a calculator. This is what you get. So we have two different approximations. Let's come up with one more type of approximation called a midpoint approximation. And this time we're going to use rectangles that have the midpoint of their top edge on the graph of y equals x squared. It's called a midpoint approximation. I don't have a nice picture for this. But again, notice that the intervals are still the same, right? But what we're doing is, instead of using the right endpoint or the left endpoint, we're going to use the midpoint of the interval. And the midpoint of an interval is just the average of the left and right endpoints, right? That's the definition of a midpoint, is an average, right? It's x1 plus x2 over 2, right? So the widths are still 1/4, right? Oh, that should be an m. Sorry, that's a typo. That should be an m. I'll fix it. But the height is the function evaluated at the midpoint. So what's halfway between 0 and 1/4? Well, it's just 0 plus 1/4 divided by 2, which is 1/8. What about here? Well, it's just 1/4 plus 1/2 divided by 2. So there's the midpoints. And when you evaluate this, same sort of thing, right? Pull the 1/4 out front, square everything because our function's x squared. We get a number 0.328125. So the question becomes, which of these approximations do you think is best? And what happens if we want to do like 100 rectangles? This would be awful, right? So based on your answers for the first 3 examples, estimate the actual value of the area under the curve. And what happens to this estimate as the number of rectangles is increased? So here's our left endpoint and right endpoint approximations, along with the areas that they generated. And we can see that this is an overestimate. There's all this extra height, this extra area. And here, this is an underestimate. There's all this missing area. But the midpoint approximation was between those two numbers, right? Because the midpoint approximation underestimates some parts and overestimates others, right? Because if it's a midpoint, it kind of goes, the function cuts through the center, so it's going to underestimate part and overestimate parts. So the midpoint approximation should be the best approximation. And should be around 0.33. So I just rounded it to 2 decimal places. And we would expect the approximation to become more accurate as the number of rectangles is increased. So that's what we're going to talk about next, is what happens as we start increasing the number of rectangles. So the picture on the left has 30 rectangles, the one on the right has 50, and these are right endpoint approximations. So notice there's this extra area here. Here, this is less area. So the question to you is, does it appear that this is converging on a specific value? So if we were to take a right endpoint approximation and let n go to infinity, what would this r turn into? What would this number go to? Because we can see it's getting smaller. Here it's 0.35, here it's 0.34. How small can it get? Well, it can't get smaller than the left endpoint approximation, because the left endpoint approximation doesn't have any extra. It's an underestimate for all values of n. But this is as you increase, the approximation gets better. So think about what's going on here. The right endpoint approximations are getting smaller. The left endpoint approximations are getting bigger. Are they approaching the same number? That's something I want you to think about. Because it turns out they are approaching the same number, but it doesn't need to be obvious that that's happening. You just have to believe that as we keep adding rectangles, the amount missing in the left endpoint and the amount of extra in the right endpoint, the limit goes to 0. So remember our definition of a limit. It's an epsilon delta proof, basically, except with infinity. It just means if you set a value for what you think that extra rectangle is on the top here, if you set a number for that, we can find an n big enough to get that number below that epsilon boundary. Right? So we're using the definition of limits at infinity here, the epsilon delta definition. It's not a delta, but it's an n, but you know, you guys actually did epsilon delta proof, so it's easier to think of it that way. So it turns out, because these numbers are approaching the same value, that is how we're going to define the area. So the area is the limit of the sums of the approximating rectangles. So what we have here is basically a squeeze theorem type of thing, right? Because both of these things are approaching the same value, that the midpoint approximation is also in there. We don't use the midpoint approximation that much because it's harder to work with when we do limits, but it's also in there. So because these limits are equal, we're going to work with the right endpoint approximation moving forward. Whenever we do limits, we're going to use Rn. The arithmetic is actually easier than using the left endpoint approximation, but you do get the same answer. So how do we use Rn to compute an area? So this is just a general method. We're going to go back and compute the area that we did in examples 1, 2, and 3. We're going to go back and do that again. But first we want to define what it means to compute an area. So let's make sure we're all on board with what's going on here, because this is actually quite technical. I'm not going through all the technical details either. I'm just going through the ones that I think are important for you guys. So if we just have any shaped region, S, we subdivide it into n strips of equal width. So it turns out it's not required that they're equal width, but it's certainly easier to compute them if they're equally width, right? So the width of each of the n strips is delta x. That's what we're calling it. This is a formula. B minus A over n. So right endpoint minus left endpoint divided by n, it tells you the width of each strip. Okay? Because B minus A gives you the total distance, and divide it up into n equal size parts. So these strips divide the interval AB into n subintervals. And they're listed below, right? x0 to x1, x1 to x2, blah, 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 xn minus 1 to xn. And we're calling x0, we're just calling it A. It doesn't matter which one you call it. We're just saying that the left endpoint of the subinterval is also the left endpoint of our interval. And xn is B, so the right endpoint of this subinterval is also the right endpoint of the entire interval. So the right endpoints of each of the subintervals, so what is x1? How do we find x1? Well, it's just A plus delta x, right? So delta x is the width, so it's just A plus delta x. What about x2? Well, we could say it's x1 plus delta x, but we don't want to have to use these intermediate values to compute each other. Let's just use A and delta x to generate all the numbers. So x2 is just A plus 2 delta x. And then any xi, doesn't matter, that's just your index, just any number down there, is A plus I delta x. Then what we do is we just take a generic strip in the middle and call it the ith strip. So let's look at its height, right? So for any rectangle, we already know its height is going to be f of xi. So if you're talking about this interval here, it's f of x1, f of x2. It's just the right endpoint of any interval. And for the last one, it would be f of b, or f of xn if you want. Doesn't matter what you call it. So S is approximated by the sum of these areas. So Rn is f of x1 delta x plus f of x2 times delta x, right? Now keep in mind, we already know what these xi's are, right? These xi's are given by this. So we're going to be able to simplify, instead of filling in x1, x2, xn, instead of putting in numbers, we can actually just replace those x1, x2, and xn with the formula a plus delta x. And what you end up with is a formula that looks like this. So this is the definition. This is what we're going to do moving forward. So before we get into it, I'm going to do one example all the way through. Some of these examples get pretty hairy. I just didn't want to make videos that take an hour, okay? When you guys watch this video, make sure you can do all the problems in this video, in the PowerPoints. When you're ready to start the homework, don't be in a big hurry. You've got to go through and make sure you're checking all these conditions. Because there's so much arithmetic, as you'll see, and the problem I'm doing in the notes here is actually one of the easier ones. Because there's so much arithmetic, if you make a mistake, you won't catch it. You've got to be super duper organized. So when you guys start doing this stuff, if you want me to make more videos of some of the homework from this section and the next section, I will. But it's going to be a separate video. I didn't want it to be part of the lecture. All right, so the area, we're just calling it the limit as n goes to infinity of Rn. Right, so we're just saying you take the right endpoint approximation and you just increase the number of rectangles without limit. Well, that's this limit, right? This is the formula we got on the previous page, previous slide. And this simplifies to summation notation, right? Because we want to write things compactly. And we can even make two further substitutions. Remember, B will be given in the problem. A will be given in the problem. Right? And then, so this will be just like a number divided by n for delta x. And then here, a is a number, I is an index, so that'll be in here somewhere. And so when we take the sum, the summation over the i's, we're going to get a formula for that. All right, so let's use that formula to show that the area under this curve is 1/3. So that might seem surprising. If you guys haven't seen this before, you might think, wait, what? The area under x squared is 1/3? Like, where'd that 3 come from? You'll see. Okay, so we need to build the summation using the definition. So we have to use all these pieces and build this thing from scratch every single time. For this particular example, I wanted the arithmetic to be easy so that the video looked good. So B is 1, our left endpoint, right? Remember, we're doing this. So A is 0, B is 1, right? And our function is x squared. So what we do is we just plug in all the known values, right? So look here, A0, B1. F of xi, our function is x squared, so we just write xi squared, right? So xi is a plus I delta x, right? But what I'm saying here is that the function itself is x squared. So whatever your xi function is, you plug that in. So you're going to see how this works when we get into it. So delta x, b minus a over n, is just 1 over n. And the xi's is a plus I times delta x. Delta x we already know is 1 over n. This whole thing simplifies to 1 over n. Now we fill everything into the formula. So look, let's go back and look. F of xi and delta x. So f of xi is xi squared. Xi is I over n. So the function itself is going to be I over n squared. So this is f of xi. You just have to keep back substituting. This entire expression, when you're ready to do the problem, can have only n's and i's in it. It can't have any x's in it, or you won't be able to do it. So you have to substitute all the x's out. And then the delta x, sorry, I went back. So here's delta x, it's just 1 over n. Then you need to simplify. So I distributed everything. So I squared times 1 is I squared. N squared times n is n cubed in a denominator. So I pulled the 1 over n cubed out. You're not allowed to pull it out front of the limit, but you are allowed to pull it out front of the summation. Is just the sum of the I squared. So now this looks like a problem from the previous section, where we just replace this with one of the formulas from Appendix E. All right, so this whole summation gets replaced with its numerical equivalent. Then we simplify, and you're allowed to simplify this however you want. There's no right way to do this. I've just factored it to make the algebra easy. You're allowed to do it however you want. So I pulled all the constants out. I pulled the 1/6 out. And then I just lined up all the terms that had n's in them, because that way I don't have to divide through by the highest power in the denominator. I can just simplify. And then these limits are real easy from here. So the limit as n goes to infinity of this is 0 and this is 0. So it's 1/6 times 1 plus 0 times 2 plus 0, which is a third. And you're done. So this is by far the easiest problem like this that you'll see probably. But every problem on the homework's a little bit different, because you might have left and right endpoints. Your function might not be x squared. It might be x squared plus 6x or something. There's a lot going on, and we're actually going to revisit this more in the next section as well. Okay, this is still just an introduction. All right, so that's the main stuff, but I just want to go over a few more details that are just factual. Okay, this is the kind of stuff that can show up as a true-false or something on a test, as you know. So it can be shown that we get the same values if we use the left endpoints. Because when n goes to infinity, it doesn't matter if you're on the left endpoint or the right endpoint. Those get closer and closer together. So if you wanted to do a left endpoint approximation, you could. But look here, it's not f of xi anymore. It's f of xi minus 1. So there's a little like fudge factor in there. So we don't use the left endpoints for these infinite limits. But it is the same answer. So the way that this is done in the real world, so the examples we're seeing are really simple. When we did epsilon delta proofs back in chapter 1, we actually did the easier ones. If you go flip through the textbook, you'll see that there was a lot of tougher ones we didn't go near. Well, that's kind of what's going on here. There's way more advanced ways to find areas under curves that work in more different situations. We're pretty much only going to look at really nice functions like polynomials. But it turns out that this technique does work for any function. So instead of using ln or rn, or even the midpoint, we could take the height of the ith rectangle to be the value of f at any number xi star. So this is an asterisk, but we call it a star. So this number is called xi star, and this is called a sample point. So the idea is that any interval, you're allowed to pick any point in the interval and make that the height of the function in the interval. That's called a sample point. So this is actually the more general definition. Okay, so this is the general version of the area. The area definition we saw earlier is the one we're going to use to solve problems. But this is how it's done at a much higher level. So I'm just giving you guys like a peek into the higher level of math. For those of you who are math or science majors, being exposed to this will help when you get to other calculus classes or differential equations. So this looks just like what we saw before, except instead of f of xi, it's f of xi star. So instead of the right endpoint, it's any point in the interval, is what that's saying. Right? The xi star are sample points. And there's actually an equivalent definition to say that a is the unique number that is smaller than all the upper sums and larger than all of its lower sums. So in example 4, we saw that a equals 1/3 was trapped between ln and rn, right? Lower and upper. And that's another way to do this. So it might turn out that maybe in the future you're working on an application where using left or right endpoints is inconvenient. But maybe there are easier values in the intervals that you'd rather use. So that's what this is showing here. So what's going on here is that a left and right endpoint approximation are built for each interval. And you choose the f of xi so that f of xi star is the minimum and maximum value of f on the ith subinterval. Right? So you just pick one set of f of xi star, that's the lowest point, and go through and pick another one that's the biggest point. And what you do is you build like an error. This is sort of like the top part of this is the overestimate and the bottom part's the underestimate. So anything down here we know is correct, but these are sort of errors. And as you make more rectangles, that error goes away. That's the idea. All right. So now there's one more type of problem that comes up in this section, and it's called the distance problem. It's just like we did velocity when we talked about the MPQ functions way back in chapter 1. This is really kind of the same thing. Find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. If the velocity remains constant, then the distance problem is easy to solve by means of distance equals velocity times time. But what if the velocity is changing? So suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them in a table. So can we figure out how far we've driven, roughly, by just knowing the speed? And not the instantaneous speed, just every 5 seconds. We're just estimating. So what we do is we convert miles per hour to feet per second, right? 1 mile per hour is 5,280 divided by 3,600 feet per second. So we just round everything to the nearest whole number feet per second. We're just trying to get an estimate on this. So during the first 5 seconds, the velocity doesn't change very much. So we can estimate the distance traveled during that time by assuming the velocity is constant. Right? That's how it works, right? So we're basically saying, in this first 5 seconds, so it goes from 25 to 31, but over this first 5-second interval, we're basically assuming it's constant. So let's say we want to do a left endpoint approximation. So then we use 25 feet per second for 5 seconds, which is 125 feet. So during the first 5 seconds, the car traveled 125 feet. During the second time interval, we take the average velocity to be the velocity when t equals 5 seconds. So the interval is 0 to 5, 5 to 10. So on our second interval, the left endpoint is 5. And so it's 31 feet per second times 5 seconds is 155 feet. And if we add similar estimates for the other time intervals, we get an estimate for the total distance. So 1,130 feet. But we know that that's an underestimate, right? We could have used the velocity at the end of each time period instead of the beginning, and you'd get a like a right endpoint approximation, which gives you 1,210 feet. And if we had wanted a more accurate estimate, we could have taken velocity readings every 2 seconds or even every second. But at some point, it's just your estimate is sort of accurate enough, right? So in general, if an object moves with a velocity given by a function on a closed interval of time, and the function has to be greater than 0, right? So we're assuming no negative velocity. We just don't know what to do with negative velocity yet. We take velocity readings at times t0, t1, t2, all the way up to tn, so that the velocity is approximately constant on each subinterval. If these times are equally spaced, then the time between consecutive readings is delta t equals b minus a over n. Notice that's the same as our delta x. So all we're doing is building the same sort of summation, but we're using t instead of x. During the first time interval, the velocity is approximately f of t0, and so the distance traveled is f of t0 delta t. And that's what we did earlier in this example. And you can see that we're building the same sort of summations that we saw earlier, right? The distance traveled during the second time interval is f of t1 delta t, and the total distance traveled during the time interval. You just sum up all of these things. And that's what we did before, right? We had 25 times 5 plus 31 times 5, right? And you just get a sum. And if you use the right endpoints, you get probably a different sum. The more frequently we measure the velocity, the more accurate our estimates become. So it seems believable that the exact distance d is the limit of these expressions. So this is the left endpoint and right endpoint. So this is the exact same thing we saw earlier with the area, where we took the limit of the left endpoint approximation and the limit of the right. We're doing the same thing here with our velocity function. And it turns out you get the exact same concept. It just looks different. So let's use this, and we're actually going to do a midpoint approximation. So here we have a velocity graph of a braking car is shown. So the car is slowing down, right? And we want to use this to estimate the distance traveled by the car while the brakes are applied. But again, it's slowing down, but its velocity is positive, right? It's moving forward. So we're just going to use the formula, right? So we have 6 subintervals, because we were doing M6. So our subintervals are 0 to 1, 1 to 2, 2 to 3, 3 to 4, 5 to 6. 4 to 5, and 5 to 6. So we need to find this. So Ti is the midpoint of the ith subinterval. So you could call it Ti star, but we're just calling it the midpoint of the interval, okay? I'm not going to get all bent out of shape about notation on this. And delta t, that's the width of each rectangle. That's b minus a over n, which is just 1. So we're going to be multiplying by 1, so I'm just not going to show that. When you guys are working at home, just if delta t is like 0.5 or something, just factor it out and multiply it through at the end. So delta t is 1, so I didn't write it here. So we have f of 0.5. Again, it's just we're doing midpoints. So we're evaluating the function in the middle of each of these intervals. So the midpoint of 0 and 1 is 0.5. The midpoint of 1 and 2 is 1.5, etc. So what is the function at 0.5? So you go here to 0.5 and you go up, and it looks like it's about 55. What about the function at 1.5? Looks like it's right there. Looks like it's about 40. And go up there. It looks like it's about 27. And 3.5. What is that? About 18. It's hard to tell. 4.5. Looks like it's about 10. And the last one looks like it's about 5. Add it all up, you get 155 feet. And that's how you do it. So this is, you have another problem like this on the homework. I would highly recommend you use this technique. if I go through this much detail in the notes, you know I'm going to put something like this on an exam. You guys kind of know my habits by now. Make sure you know this technique. It's very easy to use. It's very graphical, and I'm going to want you to sketch it and everything. So if I put on test. Well, that's it for today's lecture. If you guys have any questions, as always, you can post something on the discussion board or email me. And until next time, I'll see you guys later. And bye-bye now.